So, Preet, Inder, Singh, Rihan is going to do his MS thesis, and the committee members are myself, Wandu, and Hassan. And from what I can tell, for the last several weeks, either an honorary defense candidate or a co-advisor is Sushovan, because he seems to be going through a lot more work than any of us did. So, go ahead.
Thank you, everyone. I would like to welcome my advisor, Professor Subbarao Kamapati, committee members, Professor Handiu and Professor Hassan. So I'm going to present my work that I have done in my master's thesis. So the topic of my thesis is utility of considering multiple alternative rectifications in data cleaning. It's a well-known fact that data is one of the most useful resources available today. It's being used in many decision-making processes and many analysis processes. The validity of all those data-centric processes depend highly upon the on how clean is the data is. So, but in the current scenario, when we are dealing with the high volume and high variety and high velocity of the data, that's in the big data scenario, the possibility that we will get the clean data is very less. So we can get the clean data, but the clean data will have, but the data will have mostly the noise in it. There could be many reasons for the noise in the data. For example, the imperfect sensing devices, the information extractor that we are using, their imperfect working, and the heterogeneity in the data resources. As well, when you are entering the data, there could be errors like misspelling and all. All these data which have the quality issues is called dirty data. So here's the example of the dirty data. In this table, I'm showing the 3 dirty tuples. The first tuple has an error which is due to the incompleteness of the attributes, and the second tuple has the error due to inconsistency. Since there is no Honda Corolla car, it should be either Honda Civic or it should be either Toyota Corolla. And the third is the misspelling error that occurred into while entering the data. So now the data cleaning problem is seen as a set of problems. One problem deals with the deduplication, the other problem deals with the inconsistencies, and the other problem may tries to resolve the schema noise. There are some tools in the industry which handles the anomalies present in the database. These tools are basically known as ETL tool, and they are used in data warehousing mainly. So these Informatica, Oracle, warehouse builders are some of the vendors of the ETL tools. Apart from that, in the academics, we have techniques such as outlier detection, which detects the noise as an outlier and tries to remove the noise, and the conditional functional dependency, which actually tries to identify the inconsistencies in the data and tries to remove by learning the conditional function dependency from the clean data, whereas basewipe is another technique which tries to resolve the error due to inconsistencies, incompleteness, and substitution. So what is common between all these techniques is their approach. So what they do, they actually consider multiple rectification for a particular dirty data object, and they, after considering the rectification, they pick the most likely rectification. How will they pick the most likely rectifications? They will use some fixed rule or either the domain expert. In case of outlier detection, the most likely rectification is picked based upon the distance of that particular data object. From conditional function dependencies, they use a min cover based minimum cost function algorithm that they use to pick the most likely rectification for a dirty data. Whereas basewipe use the relevance probability that it gives to the multiple rectification and picks the rectification which has the highest relevance probability. So as I told you before, they'll pick only one rectification. So here's the problem. For example, this is a dirty data. When a data cleaning technique will try to clean this tuple, which has a true tuple as Toyota Corolla instead of Honda Corolla, it will consider two rectifications. The rectification one is Honda Civic and the rectification one is Toyota Corolla. Rectification 2 is Toyota Corolla. But based upon their fixed rule that the data cleaning techniques are used, they can give the more likelihood to this particular rectification which has Honda Civic in it. So here instead we have here, even though we have the true rectification, the data cleaning technique may choose to ignore that true rectification and may go with the other rectification that is not true. That's why the result that we'll get will be wrong for that particular dirty tuple. So due to this, the reason of this is very hard to get perfect rule which can be used in every condition to get the rectification which is true in all the cases. So if you use the partial rule, you may end up choosing the rectification which is not right, and this will result in information loss. And this information loss becomes very severe when you are actually decoupling the original data from the cleaned outcome of the data. So alternatively, what can we do? So in another approach, we can keep all rectification of a particular data instance into a probabilistic database. The probability of that every rectification can be taken from the most likelihood formulas of the data cleaning techniques. So this has the following advantage: it will prevent the information loss that occurs due to the ignorance of the true rectification tuple. Also, when this probabilistic database is used as a data source, it will produce a query result which will have more recalls. But considering this approach is not so easy, there are some challenges associated with this approach. For example, there could be too many irrelevant rectifications stored into the probabilistic database, and when that probabilistic database is used, you will get the results that will have a low precision value. Also, query processing over the probabilistic database is not as efficient as the query processing over the deterministic database. Similarly, the size of the probabilistic database will always be a problem, since the size of the probabilistic database can go exponentially larger than the normal deterministic database, which considers only one rectification for a dirty data. So in my thesis, I'm going to investigate the trade-offs of considering multiple alternative rectifications of a dirty data instance against picking only one rectification for a dirty data instance. So now I'll generate the deterministic and the probabilistic clean outcomes. For my investigation, I used a system called base wipe. So base wipe is an end-to-end probabilistic data cleaning system, and it works with the structured data. It tries to clean the inconsistencies, incompleteness, and substitution error that happens in the dirty data. The other reason that we chose the base wipe is, first, it will directly give you the relevance probability, so we don't have to calculate the probabilities from the likelihood of the rectification. The second, the base wipe is developed inside our lab, so I have the full control over the system and I can see what is happening when the system produces the outcomes. So how this base wipe will work: for every tuple T in the dirty database, base wipe will generate a set of rectifications. Those rectifications are called T star. So every T star is given a relevance probability, that is the P T star given T, and this probability shows base wipe's confidence in claiming that T star is the actual true version of the tuple T. So I use base-wise to produce the deterministic outcome as well as to produce the probabilistic outcome. So deterministic outcome which is produced from the base-wise is called base-wise DET, and the probabilistic outcome that is produced from the base-wise is called base-wise PDB. So when base-wise tries to clean a tuple T, it generates a multiple rectifications for that tuple T, and those rectifications, as I explained earlier, is called T stars. So for deterministic base-wise results outcomes, I'll choose a tuple that has the highest probability and store that tuple as the most likely tuple into the deterministic database. Whereas I'll consider all the rectifications with their probability into the probabilistic database that I'm calling base-wise PDB. So here is the example of a sample set of the dirty database that is cleaned by base-wise, and base-wise will generate a deterministic outcome for this dirty database, and it will have the same size as that of the dirty data. Whereas this is the outcome that base-wise generate, and this outcome is probabilistic in nature since one tuple can have multiple rectifications for that. So since base-wise PDB is a probabilistic database, there are different kinds of the probabilistic database. First is tuple independent, the other is block independent disjoint, and the third one is C tables. The type of probabilistic database that we have here in base-wise PDB is a block independent disjoint type of probabilistic database. In block independent disjoint type of probabilistic database, the tuples are divided into the blocks, and every tuples inside the blocks are mutually exclusive from each other, and every tuple that is outside that block is independent from the tuple inside the blocks. For example, here is the demonstration of the block independent disjoint probabilistic database. Here we have two blocks. The first block has the tuple ID 12 and the another block has the tuple ID 210. So every tuple in the first block is mutually exclusive from each other, but they are independent from the tuple present in the other block. In order to store the probabilistic database that I generate from the base-wise, I use a relational database and store them. In this case, the relational database that is being used is SQL Server. In order to process query over the probabilistic database, a probabilistic database management system is used. That's a prototype of probabilistic database management system developed at the University of Washington. It's called Mystique. So now I'm going to present how I'm going to investigate these two separate outcomes that I have created from the base-wise. So in order to compare the probabilistic outcome with the deterministic outcome, I am using two separate criteria. First criteria is the accuracy of the query results, and the second criteria is the scalability. So accuracy of the query result. Since the objective of every data cleaning approach is to provide the high quality data that can be used to provide the better query result to the user. So I am checking whether we can use base-wise PDB over base-wise DET, that is the probabilistic outcome from the base-wise, instead of the deterministic outcome from the base-wise, and can we get the better results from base-wise PDB. So in order to check that, I am checking the queries results of the base-wise PDB and the query results from the base-wise DET on four different measures. First measure is the standard precision of the query results. The second is another standard measure that's called recall. The third and fourth measures are the non-normalized measures that I'm using just to demonstrate how better the results, or how are the results when it is combined over multiple queries. So these two matrices are total increase in true positive result that will get for the multiple queries, and the total increase into the false positive that will get for the other multiple queries. So, but this, in order to get the accuracy of the query results, first we have to understand what are the query results from base-wide DET and from base-wide PDB. They are different in nature. For example, in case of base-wide DET, that is the deterministic outcome of the base-wide, when you run a query over that, you will get the deterministic results. These deterministic results will have a set of deterministic tuples. Whereas when you get the results from the probabilistic outcome of the base-wide, the result that you will get is probabilistic in nature. So, in what I mean, the probabilistic in nature, every tuple that is present in the results will have a probability associated with it. Since we are storing multiple rectifications of a particular tuple into the probabilistic database, we can also get the multiple rectifications of the same tuples into the query results. For example, here for the selection query like make is equal to Honda, I am getting 2 rectification from the tuple 3. So, in order to calculate the precision and recall, we have to first come up with some standards. So, for example, if you try to compute the precision and recall, it's not very straightforward. There are some challenges associated with it. For example, first we need to define what tuple that is present in the outcome results are relevant and what tuples are not relevant. Secondly, the precision and recall over the probabilistic query results needs to be defined. So, in order to define the relevance or the accuracy of the resultant tuple, I am going to demonstrate this example that will tell that how I am going to compute a relevance of a particular tuple. Here, a tuple will be true if the same tuple will get into the observed result as well as the same tuple will get into the result that I will get from the ground truth result. But if you see this tuple number 3 and you will look for the corresponding tuple into the ground truth results for its relevance or irrelevance, you will see that the tuple 3 is actually present into the ground truth results. But when you go one step ahead, you will see that although these tuples are present, but not every attribute of this tuple is same. For example, the tuple 3 has an attribute of drivetrain different from the observed result, and ground truth tuple has a different attributes. Here, this is a problem with every data cleaning system that first tries to identify the problem and then tries to clean that problem. Maybe this data cleaning system have over cleaned that drivetrain, or maybe it could not identify the drivetrain at the first place. So should we consider this tuple 3 as a true positive, or should we consider this tuple 3 as a false positive? In this case, we are considering this tuple as true positive if it gives us the same value for the query condition attributes. For example, here the query condition was make is equal to Honda, and I know that the tuple 3 has a make equal to Honda, and the tuple 3 in the observed result also have the make equal to Honda. I will consider this tuple as a true positive result. So, in order to get the relevance of the resulting tuple, I am defining the relevance in terms of the tuple ID. Since tuple ID do not have the noise in it, so we can use the tuple ID as the primary attribute for that tuple to get identified. And if we have the tuple ID with the same condition, same value of the query condition attributes, and the tuple IDs present into the ground truth results, will say that tuple is a true positive result. So this is true in the case of probabilistic result as well as in case of the deterministic result. So a tuple in the probabilistic result or a tuple in the deterministic results will be set relevant if its tuple ID is present in the ground truth as well. So now there is a problem associated with the computation of the precision and the recall of the probabilistic query results. Since probabilistic query results do not have the standard precision and recall defined for them, so we need to define these precision and recall in order to compute the precision and recall. Computation of the precision and recall over the probabilistic query results is not so simple. If you want to get the true precision and the true recall of the probabilistic query results, you have to compute them over these all possible words. And a possible word is a state of the probabilistic database in which every random variable is given a particular value. So in this case, if I have to calculate the precision and the recall over all possible words, how will I get the overall precision or the recall? I have to get the weighted sum of the precision and recall in order to get the overall precision of probabilistic query results. But in probabilistic databases, there are exponential numbers of possible words. So precision and the recall computation is not so simple if you want to go for the true precision and recall. So we have to come up with an approximate precision recall of the probabilistic query results. There could be two ways to approximate this precision and recall computation. The first way is just to consider the partial belongingness of the tuple. The partial belongingness of the tuples, when I said a tuple is given by the probability of that probabilistic tuple. You sum up the probability of all true positive results and divide them with this sum of probability of true positive result plus probability of false positive result. You will get the precision. Similarly, you can compute the recall by changing the denominators. And the second approach that can be used to approximate the probabilistic query results is to use a pass threshold that will classify the probabilistic results into the query results or not query results. So once we have the query result that pass that particular threshold value, we can use the standard deterministic method to compute the result of precision and recall. So this is actually the traditional way in which the uncertain results are handled. So we are going to follow the second approximation method. So now we have to put a threshold value over the probabilities of probabilistic tuple. Since in the probabilistic tuple you can have more than one rectification of a particular tuple, we need to get the aggregated probability of that probabilistic tuple. For example, in this case, the tuple 3 has two rectification. So we need to get the overall probabilities. That is the aggregation of the probabilities of every rectification for tuple 3. We are only concerned about the tuple IDs, so we'll project out only the tuple ID and the total probabilities. So after that, we'll put a pass threshold. In this example, the pass threshold is 0.2, and when that pass threshold is put, we remove all those probabilistic tuple from this aggregated probabilistic result which have the threshold less than 0.2, and we consider these results as the deterministic results and then compute the precision and recall using the deterministic precision and recall formulas. So the other criteria that the results of probabilistic the results of base weight is going to be compared is the criteria of scalability. It is a well-known fact that base-wise PDB will have a bigger data size as that of the deterministic version of that particular clean outcome, but it is worthwhile checking that what is the worst time complexity or what is the worst performance that we'll get from the base-wise PDB over the base-wise DET. So for that I am actually using two different comparisons. The first comparison will compare the size of the probabilistic database with the size of the deterministic database. These probabilistic database and the deterministic database are the outcomes from the base-wise system. And also I am going to compare the average query processing time over base-wise PDB and the average query processing time over the base-wise DET. So as the data size increase, it is observed that base-wise tries to base-wise will generate the more number of T stars for that for a particular T. So, and since there can be only one true version, so that means that we are storing too many irrelevant rectification into our probabilistic database. This can cause two potential issues. One issue is related to the accuracy and another issue is related to the scalability. When you see, when you run a query on the probabilistic database, you may get many irrelevant results. Those results will actually corrupt the accuracy of the query results. One way to handle that is to put a good threshold over that and then prune all the results which are noisy by that threshold value. And the other issue that you will face is the scalability issue. The size of the probabilistic database will become too larger as well as the query processing time will become higher. So in order to handle these two these potential issues, we came up with an optimization technique. Since we know the reason of these potential issues are too many irrelevant results present in the base-wise PDB, so we try to minimize those irrelevant results that are present into the base-wise PDB. For that, we are using a technique called pre-pruning. This is an optimization technique that actually prevents too many irrelevant tuples to get stored into the database. How will this approach work? This approach will consider every alternative rectification for a tuple T and then run a test that is given by pre-pruning algorithm, and whichever tuple passes that test will be stored into the base-wise PDB. So here's how I'm going to do the test for every T stars. So the first criteria that we are going to distinguish the tuples is the relevance probability that base-wise will generate for that particular tuple T star. So we have two separate thresholds for that. Every rectification that has a probability value less than this threshold value alpha will be rejected. This alpha is set low so that it will remove the irrelevant noisy tuple. Also, the rectification which will have the probability value greater than this another threshold beta will be considered into the accepted categories and they will be stored directly into the probabilistic database. The tuples which have the probabilities lies between alpha and beta will be considered further. So in order to consider those tuples, we actually compare their prior values. So if a prior of the rectification is higher than the prior of the tuple under investigation, we will consider that tuple to be relevant, and we will store that tuple into the probabilistic database. So we are using a fixed value called gamma here. So the reason why we are using this based upon the prior is the fact that base wipe sometimes could not identify the corruption in the legitimate tuples when they are very rare in quantity. For example, if we have very few BMW cars, and if some corruption happens in those BMW cars, base wipe sometimes base wipe would not give the actual probability to the true tuples. That's why we are using this prior based comparison in order to distinguish the relevant and the irrelevant tuples. So the value of alpha, beta and gamma are set to 0.009, 0.5 and 5 respectively. These values are set by the observation. Now I am going to show to you the experiment results that I have done for this investigation. In order to do the investigation, I performed the investigation on the used car data set that is crawled from the Google base. This database is clean as per as our information, and in order to compute in order to do the investigation, we introduce the synthetic noise into it. The noise level varies from 1% to 20%. The size of the database that we are considering is also from 1000 to 30,000 tuples. In order to perform the queries over the base-wide PDB and base-wide DET, we are choosing we chose a separate algorithm that will give us the random queries, and we'll run those random queries over base-wide DET and base-wide PDB. In these experiments results, I am going to present the result that I have got for after comparing base-wide PDB with base-wide DET on the scale of accuracy and the scalability. I'll also show that how the optimization techniques has improved the base-wide PDB performance. So if you see in this case, we have recall on the upper graph and the precision on the lower graph. For the queries like these three queries, you will see that there is a significant improvement in the recall at the cost of 0 precision. But also the precision goes significantly down in the other results, but still we have a precision in recall gain without losing the precision in some of the queries. These results, I have done it for the pass threshold is 0.1. If you change the threshold value, you can actually control the precision and the recall. For example, if you see the precision of the deterministic result and the recall of the deterministic result will be same all the time, but the precision of the base-wide PDB can change with the change in the threshold value. The precision is shown by this dark black line, and it will increase as you increase the threshold value, whereas the recall will fall down as you increase the threshold value. This threshold is the pass threshold that we are using at the time of computation of the precision and recall. So in order to compute the accuracy of the query results from the multiple random queries, it's observed that precision and recall will not give a good idea about that. So what we did, we actually compared the non-normalized matrices, and these matrices will compute the results over 100 random queries. These matrices will give us the total increase in the number of true positive generated when the 100 random queries is run on base-wide PDB and the base-wide DET. But the second matrices will give us the increase in the false positive. The increase in the true positive will tell will tell us that it is actually able to get more results, whereas the second matrix will tell us that how many irrelevant results are actually generated more. So this is the results. If you see these results, you will see that the increase in false negative, the false positive is always greater than the increase in the true positive. That means that the number of irrelevant results that is getting generated for the cost of getting more true results are more in number. So this base-wise PDB is without optimization. So we haven't done the optimization technique over this base-wise PDB. So now this graph shows us the scalability comparison of base-wise PDB with the base-wise DET. You see that base-wise DET will have the same size as that of a dirty database every case, since it is considering only one rectification, whereas the base-wise PDB will have a size that increase with the increase in noise in the data set. And you can see for 30,000 tuples, you may have to store around 350,000 tuples into the probabilistic database if you are considering the full probabilistic database. So here is the comparison of the average query processing time. This comparison is done for same 100 random queries. So the average query processing time for base-wise PDB is always higher than the query processing time for base-wise DET. The reason we can say that because since deterministic database is using a industry standard of the database management system, but the base-wise PDB is using a lab built APIs over the relational database management system. That's why we are getting this more result. The another reason is also this increase into the size of the probabilistic database. So now I'm going to compare the optimized base-wise PDB with the base-wise DET and the base-wise PDB without optimization. This blue line here shows the base-wise PDB without optimization. The another sky blue line will show the optimized base-wise PDB that is optimized after performing the pre-pruning of the base-wise PDB, and then the last line will show the base-wise DET. So if you see here in the multiple tuples, the base-wise PDB will actually increase the precision without losing anything over the recall. That means that we are able to control the irrelevant results that are getting generated as the query results. So this happens in multiple queries. In this queries, if you see that it will not affect the recall, but it will actually increase the precision, the optimization version. Similarly, in the other queries, the increase into the precision is significant at the cost of zero recall decrease. So here is the increase and the decrease into the true positive results. Increase into the true positive results and increase into the false positive results. You will see that the increase into the false positive results after performing the optimization decreases significantly. In this case, specific in this case, the decrease from this particular bar is very significant. This bar shows the increase in the false positive when you are using the full base-wise PDB, but there is a decrease into the true positive results, delta into the true positive result, but that decrease is very small in every case. So here is the improvement that base-wise PDB will get in terms of the scalability when we are using the optimization technique. In this case, if you see that the base-wise PDB when it is optimized, will give a very good, will give a very high improvement in terms of the size of the database. So for this particular tuple, when you are storing 350,000 tuples for 30,000 tuples, now you are storing around 45,000 tuples only. Similarly, the increase similarly the query processing time also decreases when you perform the optimization over the base-wide PDB. Here is the result summary. In the result summary, the left side shows the different techniques, and the right side and the upper side shows the scales on which I am going to compare this. I have compared these different techniques. So base-wide on the scale of query processing time, base-wide DET will always give you low query processing time. Base-wide PDB will give you the higher query processing time. The optimized base-wide will give you the higher query processing time, but it will be smaller than the base-wide PDB, which uses no optimization. In terms of the database size, the size of the base-wide DET will be same as that of the dirty database. The size of non-optimized base-wide PDB will be very large. As we have seen that the 350,000 tuples are being stored for 30,000 tuples only, but the optimized base-wide will increase the size of the database, but the increase is not too much. The precision of the query results from the base-wide DET will be high always. The base-wide PDB will have a high precision if you increase the pass threshold value. If you decrease it, you will get the low precision value. But for optimized base-wide PDB, the precision is observed higher or equal in almost 60% of the 65% of the cases, and 35% of the cases it is observed lower than the precision of the base-wide DET. Whereas the recall of the base-wide DET is observed low when you compare it with base-wide PDB and optimized base-wide PDB. The optimized base-wide PDB's recall decreases as you increase the pass threshold, whereas the optimized this was for the base-wide PDB, that is non-optimized. The optimized base-wide PDB will have a higher or equal recall in every case than that of base-wide DET. So in conclusion, I studied the utility of considering multiple alternative rectifications in data cleaning. For that, actually I compared two different outcomes from a data cleaning system, that's base-wide, and the outcomes I am calling is base-wide PDB and base-wide DET. The base-wide PDB will always give you better recall, no matter whether it is optimized or non-optimized, if you have put the threshold properly. But if you want a better recall, you have to lose something on the precision. Also, the base-wide PDB will lose always to base-wide DET in terms of the size of the database, also and as well as the query processing time. But the optimization technique that I have provided can minimize the cost of precision that you are giving for getting more recall. Also, it can minimize the loss due to the scalability issues. So that is what I have.
Questions? Can you put the conclusions like that? Put the conclusions like that so that people will have something to look at. So, among the three, if I have to choose one, which one?
So, you have to first decide your objective.
No, I just have to choose one. There is no precondition. Just choose one, which one?
Okay. So, I have done with the base-wide PDB, so I'll say base-wide PDB. Because now the memory is cheap and you don't care about the size, the time that you are using. You use the optimized base-wide PDB technique, you'll get the better precision and the better recall.
So it takes a higher
longer time.
Yes, it does take the longer time. That's but
You see, what's missing is when you gain something, what do you lose? When you lose something, what do you gain? It's all mixed. You still don't know. You have done a lot of work, but it would be good, you see, if it's like, for example, you said a large PDP data basis. So what? Right? You don't care, you see? Don't care. It doesn't matter. But then I think it's just like if you don't lose a lot of, if you gain a lot of precision, as you argue, but it's very vague. It's just higher or equal. It does not say, right? It's still vague. So you don't know. Still not clear. From my point of view, from this table, I don't know which one I should choose.
For that, if you have your objective as you're concerned about
No. It's not about. It's about when you have done so much, right? You should be able to let a user to take advantage of your system. That's what I want to say. At the moment, I don't. I still don't. It's only you know. I don't even know. Szechuan, do you know? Of course you know. Yeah, I mean, it's a lot of work, I know.
Because there is no clear winner. So if I say, if I'm
That's the point.
Yeah.
That's the point. You see? Then why do you do it? If there's no clear winner.
We wanted to know whether there was a clear winner or not, but it came out that there is no clear winner.
So it gives you better recall, and in some cases recall is very important to you. So if you are...
But is it easy for me to increase the recall? I just be a very lenient decision maker. I can increase the recall easily.
But then you will penalize yourself tremendously in precision.
I don't know. Yeah.
So there's no F1 measure?
I don't know. That's the point.
No, but he has some results with recall and precision.
No,
yes,
but based on whatever here.
No, that's
all,
just the summary,
every
right?
facet, right? What I want to see is like, yes, if you penalize this way, then what I gain other way. Then I can make a decision. I think you can do it. I think.
I think some F1 measure is not accurate.
No.
But I think it would also be very dependent on your database, right? On your actual
database dependent
data set that you're using.
And you didn't do anything. I give you another database. He has to repeat.
No. I'm not saying. No. I'm saying the.
You have to give me some guidance.
I understand. No, I understand. But my point is the analysis that you're talking about. I think it's very useful doing that kind of analysis. But my point is it may differ. The results of the analysis that you get. I'm not saying the system output will differ from database to database. I'm saying the useful analysis that you're suggesting. The results that are thrown out of that will differ from database to database, and that is definitely useful for the user. Because if you have, say, a car database where there are likely to be many, say, spelling errors, okay, versus you have something, a database that's curated by professionals, okay, there will be different results that you get out of both of those. I think it's definitely useful in both cases, but it's not like a single result that will come out of it, I think.
I don't get what's your point.
Basically, what he was saying that it depends on. So we wanted to check the system will behave like this only, but the measure, like how much precision that you'll lose at how much recall will depend upon the data set. You will definitely get recall better if you're using if you want to do only for the recall. You can use this value, this system, but if you are also concerned about the precision and how much that you will suffer in precision, that is totally dependent upon the data set that you have. sometimes even the base wipe results, if you give the separate data, you'll get the separate.
So, but then the argument is all about database. It's nothing to do with his techniques. If that's the case.
No, I'm saying that
we have to fix something, right? We have to fix something, then we can do something.
So I'm saying that the result is, if you want to use a system that has a high, that you are only concerned about the recalls of the results, you should definitely go with this system.
If I go for recall, then just PDT, right? PDB, right?
PDB, yes.
Yeah.
And
But
if
actually, you really don't want to say that, right? Because if you want to go for recall, just return all data.
Yeah, that's my point.
But that
it's easy to increase the recall. Recall, not issue. I mean, it's easy for me to do.
But the precision that you will lose when you give the full data will be too much. So the base wipe PDB will control the precision.
You should probably show the precision recall curve again.
Yeah.
The very first graph, I think.
Yes.
No, the one before that. Yeah.
This one, for example, in this case, if you see, you have the precision same in this case. But if you are using the base wipe PDB, your results are higher. The recall results is higher without giving anything on the precision. So here is also the same case, and here is also the same case. But with the some queries you will lose into the precision. That's true. But it's a user, if he wants to consider only the recall, the best idea to give everything to him, as you have suggested. But it will also control the precision.
No, I just tried to look into this, like a PDB, right? What's additional gain do you have? Yeah, of course you use space to change for precision, right?
Yeah.
But additional thing? Shall we get something additional from this?
So one argument is that suppose you're looking for the cheapest Honda car there is. Okay. So your criteria is, I want the minimum price. To get the minimum price, you need to have a lot of recall. Without a very large recall, you cannot be sure that you got the minimum priced car. Right? So, but a traditional data cleaning system will not care about what your criteria is for sorting. It will just see what is the best tuple I can have among all the different alternatives, and then pick that and store that. But if you do PDB, then since you have a higher recall, it is easier to get the particular car that you want without overwhelming the user with a lot of irrelevant results.
My thinking is you're already going to so much trouble to expand your database. Why don't you better use it? Yeah, think about some other ways, and a lot of work. It's good stuff.
So you worried the error between 1 and 20%, right? 1 to 20%.
Yes, in terms of the noise.
Right. So can you plot a chart that shows for example, rather than trying with random queries, so you run your correction, then you can check the precision recall at different threshold levels for different error rates.
For different error rate. Yes,
Yeah.
I can plot that graph.
So for example, then we have a prescription. Let's say I have a large database, I sample it, and I say, okay, I have like 10% error here. So then can I pick a threshold from a table and then say, okay, I will use this threshold?
So this particular graph is for 10% noise, and this is run over 15 queries.
So this is what I'm saying. We don't have to go into 15 queries. Why don't we just go back and see how much of the errors you are recovering You know, we don't have to bring the random query business into the picture, do we?
So you are suggesting a way in which we can actually compute how many tuples are, how
How
many
many of
tuples
the errors you are correctly fixing?
that is kind of the confusion matrix.
Yeah.
Okay, so I did that, but in that case, what was happening? So I defined a measure in which I say that, see, this is the tuple, and I'll consider this tuple as a true positive if it is only for the Honda and only for the query attribute, and I don't care about. I'll show you the graph. So in this case, if I have to see that how many I have computed and how many I have how many I have cleaned and how many I have overlooked, I have to see every attribute, and to draw a confusion matrix, I have to see that how many Hondas I have cleaned, how many models I have cleaned, how many car type I have cleaned, and all the stuff. But for that, if I do it in a probabilistic principle manner, I have to add the values of the probabilities. So, for example, in this case, I am adding, if it is at 0.95, I'll say that I have cleaned this with the 0.95. I'll take only 0.95 credit.
That's what I'm saying. You have
Yes.
to introduce, let's say, 10% error, and then try to see what is the best threshold for that, if there is such a thing.
So
if you can prescribe a threshold for 10% error.
So instead of going through the precision, the confusion matrix, we choose to go for the random queries method. Why is that? Because in the random queries methods, you will get the same results as that of the as if you run the random queries, full random queries, you will get the same result as that of the confusion matrix. So in the random queries, it is easier to define what is true positive and what is false positive. But the values here that we are getting, the probability values, are not the true probability values for these two tuples. Base 5 is giving us some probability values that it counts, that it generates with its own model, which has the bias. So if you count by using those probabilities, you will not guaranteed to win, or you are not guaranteed to lose, because it is not probabilistic principle from the base 5 side itself. So that's why we pick the random query method.
I have the same confusion with one. Like, you guys are not able to prescribe us a method for straightforwardly using this thing. That is why, right? So that's the problem. So it seems like the nature of the query should be taken into account to figure out what to use here. Like whether it is an aggregate query, you maximize
Yes. So this system does not work with the aggregate query. This is only for the selection when you want some selection. See, aggregation will have the same counting problem. So the counting, if it is a true probability of that tuple to be present into the real world, you can aggregate it and you will get the same results.
Also, we don't understand after what point this thing works, right? Let's say I have more than 50% error. Then do we have any idea when is it going to start producing?
So this is the graph in which you'll see that as you increase the noise, then the size of the probabilistic database will be increased.
Okay.
So if the size of the probabilistic database is increased, you are losing on terms of storing the database as well as the query processing time, because the query processing time will also increase as the size of the database will increase. So it is the way the base Y picks the T star, the rectifications to clean a particular tuple key.
So actually,
the way you just argued, you're saying almost as if you should go away from PDB as the noise increases. If the noise is low, I don't want PDB anyway. This is again, we've gone through this multiple times. Ultimately, left to yourself, you care about scalability. If you care about scalability, you shouldn't have cared about PDB.
Yes.
So you need not have done this thesis. All I'm saying is, change your mindset about the scalability stuff. Okay, before you wrote the first line of code, you knew that scalability will suck.
Yes.
In fact, probabilistic methods are exactly useful when the noise is high. But what you just said right now is, as the noise increases, PDB will be a bad guy. There is nobody who is any better. PDB is the only game in town. But what I'm saying is, the reason I think people are confused is because you are ambivalent about PDB. You don't quite believe that actually keeping multiple alternatives when you are not sure which alternative is the right one is actually the right approach to take. You're looking at the same results we are looking at, but you made up your mind. You made up your mind saying PDB is in the worst it will be just as good as debt. In which case you should be doing this thesis. In fact, the results say the opposite. The results basically say that when there is noise, PDB is the only game in town. It is actually doing better.
In terms of
but
accuracy.
You did not say that.
Yeah, in terms of accuracy, it is true.
But I think again, there were 8 different places where you put scalability before accuracy. I got you to change it. In 6 of them, there are still 2 more places left where scalability is before accuracy. Because I can't change your mind. You really wanted scalability. So you should not care about PDB in that case. It's like a fit issue. It's the thesis that you are not actually believing in yourself. I think actually when there is noise, when I'm not sure, I just sent you a mail, by the way, that there was this beautiful quote by Niels Bohr, that Niels Bohr would talk very haltingly and very uncertainly. And people would ask him, why don't you sound more sure of yourself? And he said, I try not to speak with more certainty than I think. Okay. In essence, the debt is basically saying, I will become certain even though there is humongous uncertainty in the input data. Okay. And PDB is the only game in town. And furthermore, you are not the only guy who was wondering whether PDB and debt, how does the comparison work? It's not an idle curiosity. You should have brought up, for example, you could have brought up in an answer to the query that the CRA report on big data specifically states this is a very worthwhile thing to do, and they would like to know the answer. So you're providing partial answer to them too. Okay.
I have a small question. So you have alpha and beta, right? You look at the tuple that between the confidence between alpha and beta. So how sensitive?
It's alpha and beta. Yeah, they are. So I've done the experiment with the alpha and betas as well by changing their values. The beta values is not so sensitive. So alpha value beta depends upon the probability distribution that you will get from the base vibe. So if the base vibe is very peaked, you can put the alpha like 0.8 to 0.5. And also you can use the threshold beta. I'm sorry, beta. The alpha you can use the minimum alpha, like even lower than the 0.009. But if the probability distribution that you are using, that base vibe is giving to you, is different, and it has like tuple 0.8, 0.4, 0.3, then you have to make sure that you are changing your alpha and beta values accordingly. So, but in this observations, I have seen the most of the values that base vibe is giving to me is a peaked in nature, the distribution values. So I choose the alpha and beta accordingly.
So the basically when you say the distribution is peak at one point, I mean the variance at the time is quite small.
Yeah, in the most of the cases. So you can vary the beta and alpha accordingly.
So how does beta and alpha affect your processing time?
Sorry? orders alpha, beta, and
How does the data analysis affect the query processing time?
it does. So it is not used at the query processing time. It's used before, when you are going to store the probabilistic. You are creating your probabilistic database. At that time, you are making a decision whether you have to pick that T star as a relevant rectification, and you want to store that into your probabilistic database or not. That after doing that, you will get a base-wide PDB that is an optimized version of the base-wide PDB.
But the size of the database will be different.
Yes, that's why when the size of the database is different, you'll increase, you'll get the good values in terms of the query processing time.
Any other questions? So if not, I think the public session is over. You can just stop the recording.